Hi, in this session we will be going through AWS SageMaker training with 4 GPU and 1 Spot instance using CIFAR100 dataset and a ResNet 34 model. So we will walk through how the notebook instance is created and how to execute this Python script via SageMaker notebook instance. First step is to create a notebook instance. I already have 3 notebook instances created, as you can see. So I will create one more for demonstration purpose here. I'm just creating a notebook instance and giving it a name. We need to create an IAM role. So let us create a new role. These are the specifications that you need to give. Mainly, it needs to have access to any S3 bucket. Create the role. So this will be the role that is created. And what we are doing is like we are attaching this role to the notebook instances that we just created. Go ahead and create notebook instance. Okay, notebook instance is getting created. Currently it is in pending status. It will take some time to get the notebook instance created. As you can see, we have created it in ml.t2.medium, which is the default instance that is offered to us. This is a CPU only instance. Uh, Please remember that we are going to train in GPUs. So we will be creating a training instance later in a different EC2 instance which offers GPU. As we can see, the notebook instance that we tried to create is shown as in service now. So now let us get into it and create a Jupyter notebook. I'm creating a Jupyter notebook with Conda PyTorch latest P36. Now we need to do few necessary imports. So, uh, first we are importing SageMaker library. We are creating a SageMaker session. We are using the IAM role that we attach to this Jupyter instance here. We will create an S3 bucket. We are creating a checkpoint S3 path. This will be the S3 path in which our model checkpoints will get saved. We will pip install PyTorch Lightning and pip install Google Drive downloader. Uh, this will be helpful to download something if required from G Drive. Next, we are exploring few data related items. So we are importing the CIFAR100 data module from this Python script. So before executing this script, we need to make sure that the Python script that we are planning to execute, in this case CIFAR100 PLV2, is uploaded to the Jupyter instance. So what we are doing here is like we are creating a instance called DM from the CIFAR100 data module class. We are executing the prepare data method available, which will download the CIFAR100 data from Torch Vision datasets. Then we will set it up, and then we will also create train loader and test loader with the data that we downloaded. PLV2 Pytorch Lightning script. Yeah. So this is a Python script where we will put the necessary statements to execute CIFAR100 training in PyTorch Lightning framework. Here we are doing necessary imports. We are installing PyTorch Lightning and Google Drive downloader. Google Drive downloader is used to get the model weights from Google Drive. These are Torch related imports, and these are PyTorch Lightning related imports. So this was the module that is handling data related stuff. This prepare data method will download CIFAR100 dataset from torchvision.datasets library. And this setup method is setting up the data. And with the help of the data that is being set up here, we are going to create train data loader, validation data loader, and test data loader. This is what we are seeing here. We are importing CIFAR100 data module. We are we are creating the CIFAR100 data module with a batch size of 32. We are preparing the data, which is downloading, which we can see the download progress here. Then we are using setup. Then we are defining train loader and test loader. Now let us inspect the remaining contents in this Python script. Next is creating the model. We are taking ResNet 34. Pre-trained is equal to true, which means this is pre-trained. But ResNet 34 available in Torch Vision models library is pre-trained on ImageNet. We are using CIFAR100 here, so we need to change the fully connected layer features to have 100 number of classes. So that is the change that we are doing here. And next is we are creating a PL Lightning module. We are naming it Light ResNet 34. So in PyTorch Lightning, we will define a training step where we will split the batch into images and corresponding labels. We are passing it through the forward function here to get the logits. Then we are using negative likelihood loss to calculate the loss. We are converting it to a format where we can use it to calculate the accuracy. This accuracy is a method that we have imported at the beginning from torchmetrics.functional. Then we are going to log the train loss and train accuracy. Once we are logging this using self.log, what will happen is like it will automatically appear in TensorBoard or weights and biases logger, whichever we prefer to use. Similarly, validation step also we are doing the same thing. We are having a test step also defined separately, which will use the test data loader that we created above. Then we are configuring the optimizer. We, uh, we are using SGD. If required, we can give the training cycle policies like one cycle LR. You can see the code here, but I am just returning the optimizer here. Next is train function. It will receive arguments. We can see the arguments towards the bottom of this Python script, which is kept under main guard. We can also give the arguments from SageMaker notebook, which we will see once we start using the notebook. So here we are again we are again creating a data module object. We are calling the prepare data setup methods. We are defining the model with the LightResNet 34 class that we have created above, again with a batch size. Then we are giving an early stop callback. We are monitoring for validation loss and a patience of 20. This means it will wait for 20 epochs, and if validation loss is not improving, the training will stop. And uh, actually, I have pre-trained this ResNet 34 in Google Colab and saved the weights in Google Drive. So this is the model G Drive path that I am giving, and with the help of Google Drive download, which we imported and installed at the beginning of the script, I am downloading it. And if successfully downloaded, I am loading the model defined here with the help of this weight that is being stored. This is checkpoint path. Again, when you are training for the first time, this won't be there. But if you are training for the next time in Amazon SageMaker, then there will be the checkpoint path, which will be saved in this arcs.checkpoint path. So if it is available, model will load that checkpoint and use it. Next is a trainer method. This is again something different from PyTorch. Uh, so in PyTorch Lightning, we have a trainer method defined, and we need to create a trainer. So max epochs is equal to 5. This is the number of epochs for which I am training. If we have early stop callback, this will get overridden. But I have given patience as 20, which means till 20 epochs, it will just wait. So since we are giving max epochs as 5, this early stop callback is not going to be effective here. This is progress bar refresh rate, which will show for every 20 steps what is the progress. We are using GPUs is equal to 4. Strategy is DDP. Logger that we are using is TensorBoard logger, and I'm gonna name it uh, as like this, which means the logs will get saved here. Enable model summary is equal to true. This is again another feature that is in PyTorch Lightning. We don't need to code to display the model summary. If we are giving it as true and giving max depth as -1, it will show all the uh, parameters that is being associated with each layer, like we see in PyTorch. Again, this model summary and early stop callback, these are callbacks which we need to import if we wish to use it. So then we will use trainer.fit method. We will be passing in the model as well as the data module that we created. Once this statement is executed, the model will start training for 5 epochs. Then we will execute trainer.test. Whatever data is being passed through test data loader, um, it will be evaluated once the statement is executed. After that, we will save the checkpoint. This is a inbuilt method. We will supply the args.checkpoint path and we'll be saving the checkpoint weights in this format. So this is why I was telling when we are doing it for the first time, checkpoint will not be available in this path. But once we have trained at least for one epoch, then this will get saved. And next time when we are using uh, this statement, will capture it and it will load from the checkpoint. We will also save the model. Typically, this model underscore directory is a default one, which is slash opt ml slash model. So it will take from this default. Next is a function that is defined to show the images. This we will use in our Jupyter notebook just to make sure that train loader and test loaders are working correctly and images are coming as expected. Next is model function. This function is used for inferencing. When we are calling the uh, predictor method, which we will see in Jupyter notebook, it will call model function inside this Python script. What this model function does is like it will simply load the model and it will fetch the model from model directory, which I mentioned is slash opt slash ml slash model. It will see if this model is there or not. If yes, it will load. If it is not there, then probably our inferencing will fail. And this is the main guard, which will accept the various arguments. These are the arguments that are being given. Some of these will be overridden by the arguments which we supply via Jupyter Notebook. Then we will train the then we will execute the train function, which will start executing all these things coded down here. Now reverting back to Jupyter Notebook. So I will be defining this IMShow function here as well. And this unpickle function as well here. Like I mentioned, I just want to make sure that the data is getting displayed correctly before training, because once we start training, we will incur a cost. So I just want to make sure that data part is clean before I start training with GPU. So IMShow we already explained. What unpickle does is like it will this CIFAR100 is in a pickled data format, so we need to unpickle it and get the label names and few other things. If you want to know about the dataset format of CIFAR100, just search out in Google. There should be enough documents for you to understand what this meta means and what this pickle and unpickle kind of stuff are doing. Now I am just testing out the test loader to see if the images are coming out correctly. One thing to notice is like here in test loader, in test data loader, we have given the batch size as 4, and for train and validation data loaders, it is accepting the batch size whatever is being supplied while we define the CIFAR100 data module object. We gave 32. So for train and validation data loader, batch size will be 32, whereas for test, it will be 4. Yeah. So these are the data sets and these are the class names. First one is mountain and last one is mushroom. So we just confirm that test data loader is working fine. Similarly, let us check if train data loader is also coming out correctly. We should ideally get 32 images, but I'm just showing the label names corresponding to first 8 images. Yeah, we are having 4 by 8 32 images getting displayed, and first 8 are being shown here. The first one is cup, second one is apple, third one is skyscraper, and last one it is kangaroo. Now, since we are using Google Drive download, I'm just checking whether this is working correctly or not. Looks like it is working fine. We can see the downloading message. Next step is to prepare the inputs which we will feed to the estimator that we are going to create. So this path is equal to data. Why we gave this is because we in our data module we have given the data directory as data. That is the reason we are giving the path as data. And bucket we have given the S3 bucket that we defined above. Now let us import PyTorch from SageMaker PyTorch SDK. Here we will be using Spot instances. Advantage of Spot instance is like it will give you a significant cost saving up to 65 to 70 percentage. Flip side is like if the requested instance is not available, then either we have to wait or we have to try some other time. So I'm creating a CIFAR100 estimator, an estimator here. I'm naming it as CIFAR100 estimator. So with the help of this estimator, we will execute the Python script. We are giving the role as a role that we created earlier. Framework that we are going to use is 1.71. Python version is Py3. Hyperparameters we are giving batch size as 32. So what this means is like these are the we have seen few arguments in our Python script, right? So batch size is one of the arguments there. Okay. Default for this one is 4, but by passing it through the hyperparameters, we are making it 32. Similarly, we can override any of these arguments defined here. For example, maybe momentum or model directory, whatever, or number of GPUs. We can override it here. So that is what this point signifies. I'm going to use instance count of 1. I'm going to use instance count of ml.p3.8x large. So if we look up ml.p3.8x large is having 4 GPUs. I'm just naming this base job name as Jan27. These are the 2 points that we are using for checkpointing. This checkpoint S3 path is something that we have defined at the beginning. This checkpoint local path, it is the default path that SageMaker will first store the checkpoint when we are training. What happens internally is like from this path, it will automatically copy to S3 bucket. And next time when we are training, if we are giving this checkpoint S3 path correctly, it will automatically fetch it from S3 bucket and load the model using that one. Use spot instances, we are setting it as true. And in case if we are using spot instances, we will uh, keep runtime of 1200 seconds, and we will wait for 1210 seconds to see if the spot instances that we requested are being available or not. So now, since we created it, next step is to fit it with the inputs. What are the inputs? Inputs were the data that we have provided. So what will happen is, like, once we execute this step, internally it will execute the Python script, which means we will start training and evaluating the CIFAR100 dataset with the model that we have created. So let us execute this. So it is starting the training job, and next step is to see if required instance is available or not. If instance is available, it will start downloading the data, and eventually it will start training. This will take some time because SageMaker is trying to launch the instance and try to start training. As we can see, training has started. Uh, it's downloading the input data and downloading the training image. Once that is completed, uh, training have started, which we can see by the epoch numbers listed here. You can see the checkpoint is saved. Model summary is getting displayed. Since we are having 4 GPUs used, we can see the local rank and visible devices displayed here. Model summary, since we gave max depth as -1 in our Python script, model summary is being displayed. And training is completed. So since we were using spot instance, we were built only for 110 seconds, uh, which helped us to get a savings of 70.1 percentage. Now next step is to create a predictor class. We are importing Pytorch model from SDK, and we are creating a predictor with deploy method. We are using a different instance type here. This is a CPU only instance. Reason being, for training we use GPU because amount of data that we are dealing is high. But for predictor, we don't need that heavy instance, a heavy machine. So we are going for a lighter one. It will take some time to have the predictor set up. What this is doing is, like, it will set up an endpoint also for us, which we can see from this section here. I'm creating a data iter here just to check whether the predictions are working correctly or not. So what it will do is, like, it will take the images from test loader, pass it through the predictor that we are creating here, will call inference will call inference with predict method by passing the images, numpy images, and we will get the outputs. And then we are just trying to find out whether how good our predictions are based on the supplied labels and the predicted labels. That is all what we are doing here. Once this predictor is done, we need to delete the endpoint, else there are chances that we might incur some cost. So this statement is also important. What it will do is like the endpoints that are getting created inside this. Right now yeah, it came up. So this one, it will delete it. It is not yet completed. Once this cell is completed, we can start seeing whether prediction is working correctly or not. From the logs, we can see that we have achieved a 57% test accuracy. This is mainly because we loaded our model from the pre-trained ImageNet model. Plus, as I mentioned, I have trained it in Google Colab before starting this. That is the reason why we got 57% accuracy, or else we might be just hitting some 10% accuracy. As we can see, predictor is now ready. So let us see if it is working correctly or not. Yeah. So these are the predictions. As we can see, we just got 1 out of 4 correct. Since the purpose is saved, let us delete the endpoint as well. So if we go here now, we shouldn't see anything. Yes, it is gone. And one more good practice that you can follow is like you can go and stop the notebook instance as well once you are done with the purpose. So thanks for watching.